Welcome to this video lecture on the subject of binomial and Poisson calculations. We begin with the binomial distribution. We have a formula which allows us to calculate the probability that there will be exactly R occurrences when n trials are performed. So the formula is for P brackets R, the probability that exactly R occurrences will arise. And to use this formula, we need to know n, the number of trials that are performed, small p, the probability of occurrence on each single trial, and R, the exact number of occurrences that we're interested in. The formula then provides us with the probability that there will be exactly R occurrences. And the formula, you may notice, is quite reasonable because R occurrences, if you like, are chosen out of n, and there is occurrence and occurrence and occurrence R times, giving us p to the R, and then on the other occasions there is non-occurrence, n minus R times. Here's an example where we have 10% of eggs are brown. 6 eggs are packed at random into a carton. We wish to know what is the probability that exactly 2 of those eggs are brown. In this situation, n equals 6, the number of opportunities. In this situation, p equals 0.1, that is 10%, the probability that on any one occasion a brown egg is chosen. And R equals 2. This is the question we have. What's the probability that there are 2 brown eggs in the carton? We substitute these numbers into the formula and we find that the probability that there are 2 brown eggs in the carton is 0.098415. So it's just less than 10%. It's not very likely to happen. We could, of course, have calculated the probability that there would be no brown eggs or 1 brown egg or 2 all the way up to 6. And in fact, this distribution shows the answers we would have got had we done that. The lower values, of course, are much more likely because the brown eggs are scarce in the population. If we had wanted to know the probability of there being a different number of occurrences, we could substitute that value of R into the formula. Here's the same problem, but this time it's for the number of female members on a jury, where P is 0.55, 55% of all the citizens are female, and there are 12 members on a jury. And because 0.55 is quite close to 0.5, this time the distribution looks quite close to a normal distribution. And in fact, a binomial distribution can be approximated by a normal distribution, and that can speed up the calculations. We now move on to the Poisson distribution. Our formula this time is not so intuitive. P brackets R again means the probability that there will be exactly R occurrences equals e to the minus lambda times lambda to the R over R factorial, where lambda is the mean number of occurrences per interval. And lambda, as explained, is the mean, and e is the base of natural logarithms. It's a number that's already familiar to your scientific calculator. So that formula, P brackets R, allows us to calculate the probability of exactly R occurrences in an interval. So here's an example where a company receives 3 complaints per day on average. These are random events. What is the probability of receiving more than 2 complaints on a particular day? So more than 2 means we're interested in there being 3 or 4 or 5 and so on and so on. It's an infinite list. So we cannot possibly calculate all of these values and add them together. However, if this does not occur, then there's 0 or 1 or 2 complaints. So we'll calculate P0 plus P1 plus P2. And if we subtract that result from 1, then we will know the probability that there are more than 2 complaints. So we substitute 0 into the formula and we get P0 is 0.0498. We substitute 1 into the formula and we get 0.1494. And we substitute 2 into the formula, we get P of 2 equals 0.2240. In each case, of course, substituting 3 for lambda because 3 is the mean. We add those results together, giving us 0.4232. That's the probability that there will be 0 or 1 or 2 complaints on a particular day. If that does not occur, then there will be 1 minus 0.4232, which is 0.057, rather 0.5768 is the answer to the probability that there will be more than 2 complaints on a particular day. Here's the full set of results if we calculated the probability of 0 complaints, 1 complaint, 2 complaints, and so on. And of course, the distribution continues on to the right with the values of the probability getting smaller and smaller. The graph has been stopped at 10, but of course, in theory, it continues on beyond that. But there's no particular place where we can say that it finally stops, because any number is possible, even though it has a very, very small probability as the number increases. So this is how we calculate the probabilities for a binomial or a Poisson distribution, and you can read more about this in section 3D of the textbook.